Welcome. Let's take a look at an example where we minimize the perimeter of a rectangle. So the question is, of all rectangles of area in square centimeters, which has the smallest perimeter? So let's kind of explore this through a diagram. So we have a rectangle. Typically, we think of rectangles as either in terms of base and height or length times width. Either one works. And we know that the area of this rectangle is in square centimeters. So the area in here is in square centimeters, or we could say length times width equals n. That's our area. And what we want to do is we want to find which rectangle has the smallest perimeter. That means we want to minimize the perimeter. So our goal here is to minimize the perimeter subject to the area of the triangle being in square units. So our constraint is that the rectangle must have an area that is in square units, and our objective is to minimize the perimeter. Well, if we use L and W to represent the two sides of the rectangle, then our perimeter would be 2L plus 2W. And of course, right now, we can see that our perimeter function is a function of two variables. So let's leverage the constraint function to eliminate one of the two variables. Now, it can be either one, it doesn't really matter. So I'm going to go ahead and replace W in the perimeter function, which means I need to solve for W in the area equation. And solving for W, I will have n over L, and using that information to rewrite the perimeter function, we'll have 2L plus 2 times n over L. At this point, we now have a function that is of one variable, and we can start thinking about finding its critical points and minimizing it. Before we do that, though, let's think about the domain of the function. And because we're talking about area and lengths of sides of a rectangle, we will assume that L must be greater than or equal to 0. So our perimeter function, let's go ahead and rewrite it in preparation for finding the derivative, will be 2L plus 2 times n times L to the negative 1 power. And now we can find our derivative. P prime will be 2 plus 2n times negative 1 L to the negative 2 power. So P prime equals 2 minus 2n times L to the negative 2 power. And we need to find critical points, so it might be easier to do that if I remove the negative exponent. So we have 2 minus 2n over L squared. Let's go ahead and get a common denominator so we can set our derivative equal to 0. So we'll multiply 2 by L squared over L squared. Doing that, we get P prime is equal to 2L squared minus 2n all over L squared. Now there are two sources of critical points. One will be where my P prime equals 0. The second will be where P prime is undefined or does not exist. Looking at my derivative function here, I can see that my derivative would not exist if L equals 0. However, when we look at our area formula and we need that product of length and width to equal n, L equals 0 is not a possible solution, a possible value of L, because if L is 0, then the area is 0, and we know that the area must be n. So we can disregard that critical point. So coming back to our first critical point, or first source of critical points, for p prime to equal 0, then the numerator of that function must equal 0. So we'll have 2l squared minus 2n equals 0. Add 2n to both sides of the equation. We get 2l squared equals 2n. Dividing by 2, I get L squared equals n. And then taking the square root of both sides of the equation, L equals plus or minus the square root of n. Now, again, considering we're talking about the sides of a rectangle, this negative root does not make sense. So we will focus our efforts on L equals the positive square root of n. So we have our critical point. We have not yet established that it is a minimum, that it produces a minimum. So we need to do that. If we come back up here to our first derivative, we can see that finding the second derivative of that function is not too difficult, and we could use the second derivative test to determine or to show or to demonstrate that we have a minimum. So p double prime equals 0 minus, we've got our 2n, and now the derivative of L to the negative 2 power will be negative 2L to the negative 3. So we have here is a positive 4 and an n, and the L cubed is belonging in the denominator. And now if we evaluate the second derivative at the square root of n, remember we're interested in the sign only, we'll have 4n over the square root of n cubed. Well, n is positive, it's an area. My numerator is positive, my denominator is positive, so my second derivative is positive at my critical point. If my second derivative is positive at a critical point, then I know that I have a minimum. So we have in fact found a value for L that produces a minimum. So now we need to go back and revisit our original question. That is, of all the rectangles, which has the smallest perimeter? Well, we know that L has to equal the square root of n. Now we do have information about W. We see that W equals n over L. So if L is square root of n, then W is n over the square root of n. And if I simplify that, then I have W being the square root of n. So notice that the length and the width of my rectangle are equal, meaning we have a square. So we can state our conclusion at this point that the rectangle of with area n with the smallest perimeter is a square with sides of length square root of n. I hope you find this helpful.